As usual, once you guys are done, put a green check next to your name. Only for the first question. We'll do the second one after, like we walk through prims together.
So,
Yeah, go for it.
Oh wait, I just saw you assumed ties are broken alphabetically. Never mind. I was just
Yeah.
about to ask.
Yeah, good question. Yeah, once you guys are done, put a green check. And then if you guys finish early, you guys can start the next question. Okay, so I'm gonna walk through the solution. So I'm not gonna use like the actual like edge 2 and like distance 2 and the fringe. I'll just kind of show you how to look at the graph and walk through it intuitively. I think it's a bit faster. So let's say that we start with A. Let's choose a color that we can see. Red is good. Okay. Okay. So we claim A, right? I like thinking about prims as we keep choosing the nearest vertex to join our team, okay? Who's the nearest person to join our team? G, okay? So we add G. Okay, so far we've done A, then G, right? Okay, now who do you want to add to the team? Who's the closest vertex? The closest vertex, I mean, we have a tie between B, C, and F. Who do we choose? We break ties alphabetically, so we choose B, okay? Now we add B to our team, okay? We add B to our team, and then these are the vertices that we've done so far. Let's keep track of the edges as well. So far we've added AG, right? And we've also added AB, right? Okay, so now who is the next vertex we want to add to our team? We look at all the vertices and we see which one's the nearest one. Well, C and D are both one away, but C is alphabetically superior, so we choose C. Right? Okay, let's quickly add that in. We add C, then we add BC. Okay. Now we have to add somebody else to the team. Who do we choose? Who's the closest to us? Well, we know that F and D are both one away, and D is alphabetically superior, so we choose D. Right? So this is interesting. Which edge do we choose? Someone want to shout it out?
I kind of guessed B because we were breaking ties alphabetically, but I wasn't sure.
So this is a really, really like tricky question. We're gonna choose the edge between B to D. Okay. The reason is once we go to B, we visit B first, right? So in the priority queue, right, in like the fringe that we're working with, after visiting B, we're going to add D into the fringe, right? Because we're going to update the priority of D in the fringe, right? So we're going to say that D's priority is now 1, okay? This is after visiting B, okay? Then once we visit C, we ask ourselves, is there a shorter path or is there a shorter edge from C to D than was previously there? Well, the edge is the same weight as the one that was previously there. So we don't update the priority of D because it's already like optimal. What this means is that the edge that we've recorded to get to D was the edge from B. And that's because we only change the priority of something if we figure out something that's explicitly better than what we saw before. Yeah, so then we'll add BD. That's tricky though. Okay, C. Okay, now let's keep going. Now we have F, E, and H. Who do we add? There's no ambiguity. F is the best, right? So now we could see that it'll go F, then H, right? Because H is one away. Then finally, we have to add E to the team. There's nobody else. Everybody else has been chosen. So we'll add E to the team. Okay. So quickly to finish it up, we added D, then F, H, and then E. Oh, question. What is the difference between Dijkstra's and Prim's? This is a good question. So what Dijkstra's is doing, it's building a shortest paths tree. A shortest paths tree is the shortest distance from a start vertex to all other vertices, okay? What Prim's is doing, it's creating a minimum spanning tree. A minimum spanning tree is a different entity entirely. It's not, like, I don't like to think about Dijkstra's and Prim's as similar in terms of like what they do. They're only similar in terms of how the algorithm is executed. What this means is that a minimum spanning tree is different than a shortest paths tree, okay? If we think of a shortest paths tree here, we can see that the shortest path from A to F, right, is like this. That's the shortest path from A to F. But the path in our tree that we've recorded is 2, 1, 1, right? This path is not the shortest path from A to F. So we can kind of see here that the minimum spanning tree isn't the same as the shortest paths tree, which is what Dijkstra's creates. Does that kind of make sense? Chat? Okay. So I'll quickly finish filling it all in. We added F, then H, then E, right? And in terms of edges, we added BD, then we added CF, then we added FH, then we added CE. Okay? Yeah. Okay. Does anyone have any questions? Okay, so let's move on to the next question. The next, okay, that was a quick explanation. You guys can read it if you guys want. Okay, here's the next one. Sorry. Prims can perform a change priority operation on a vertex V at most blank times and at least blank times. So take like a minute and try to think about it. Does anyone want like a more thorough explanation of how prims work before we dive into this question? If anyone says yes, I'll quickly give like an explanation of how like the fringe works. Otherwise, I'll assume that you guys have some sort of idea. Okay, yes. Okay, so I'm gonna walk through this example and I'll show you what the fringe is. Let me quickly move this. So we can think about the fringe as the vertices that we're looking at next, okay? Let's get rid of all of the stuff we've done. Okay, so when we start the algorithm, the only thing that's in the fringe is A, okay? the priority of an element in the fringe when we run prims is the shortest recorded distance from that vertex to any member of the MST. Okay, so we're going to say the priority of a vertex V is the shortest recorded distance from V to any vertex in the MST. Okay, so we're going to start off the algorithm from A. Currently, the shortest distance from all the other vertices is infinity, because we don't know anything about the shortest distance from C to the MST, because the MST doesn't exist yet, right? So the only thing we have A that's 0, and then all the other vertices are infinity. Okay. Now what we're going to do is we remove the highest priority element from the fringe. Okay. In this case, we remove A. After removing a vertex, we look at all the neighbors and we ask ourselves, do the neighbors provide new information we didn't know before, right? So after looking at A, what we do is we look at the neighbors G, C, and B, and we ask ourselves, is there new information here that we didn't know before? And for all of them, the answer is true in this case, right? We thought the shortest possible distance from G to the MST that's built so far is infinity. C infinity and B is also infinity. So now what we're going to do is we're going to say G maps to 1, C maps to 3, and B, actually, let's reverse the ordering of it. B maps to 2, right? And then C maps to 3. And what I'm saying it maps to, that's the priority of that vertex, okay? Question, yes. Go for it, Anish.
So you're saying that you look at B and C after you're done with G, but like whose neighbors do you look at a particular time? Like, do you look at A's neighbors, which is B, or do you look at G's neighbors, which is both C and B?
Yeah, good question. Whenever we remove a vertex from the fringe, then and only then do we consider the neighbors of that vertex, okay? In this case, we just removed A from the fringe, right? We removed A. So once we remove A, once we remove any vertex for that matter, we look at all of its neighbors and we ask ourselves, like, is there new information? So in this case, we only consider these 3 edges, okay? We still haven't looked beyond these 3 edges because all we know right now is the neighbors of A, okay? So after looking at the neighbors of A, right, we figure out that G has priority 1, B has priority 2, and C has priority 3, okay? Now we're done with this iteration, so we're going to repeat, right? Each time when we repeat, we take the highest priority element, which is the smallest in this case, and we remove it, okay? Now we remove G. What do we do when we remove an element? We look at all its neighbors and we ask ourselves, do we have any new information we can add to the elements in the fringe, okay? So what do we know? We know that F was currently in the fringe with priority infinity, right? So we'll add F to the fringe with priority 2. Okay. Right, and this purple line, this means like we've considered this edge. After removing G, we also have some more information about C, right? More specifically, we now know C is actually 2 away from the current MST, right? So we'll update C to now be 2, okay? And then we'll move this around. Okay. Now this is the current state of our fringe, right? We have B, C, and F. So who do we remove? Well, alphabetical superiority makes B the one that we remove, okay? So now we've added B to our MST, okay? Our MST now consists of 3 vertices, B, A, and G, and they're connected by edges B, or AG and BA, okay? So it may be redundant now. So hopefully you guys get the gist that every time we remove an element from the fringe, we look at its neighbors and we ask ourselves, do we have any more information to update the priorities of the elements in the fringe, right? So like after removing B, you would say that, well, now C's priority becomes 1. D's priority also becomes 1, right? Actually, that's the wrong one. B's currently removed from the fringe. Then we update C's priority to be 1. And then we add in D with priority 1. So that's the next iteration. Does anyone have any questions on how prims works? Okay, I'm taking that as full and complete understanding. So let's go back to, perfect. Glad to hear it, Parker. Okay, let's go back to this question about prims and changing priority. I'll give you guys like 30 seconds to think about it. Okay, for the sake of time, I'm going to take it up. Does anyone have any ideas, actually? Anyone want to be famous on the internet? Okay, I realize I scared you guys away by saying that. So the answers is that, actually, let's first like walk through the process before I tell you guys the answer. So let's say we have some vertex, right? Let's say the vertex C. Okay, what's the maximum number of times that we can perform a change priority operation? Well, let's think about it. Whenever we look at an edge going into C, that edge could potentially give us new information we didn't know before, right? So looking at C, right, if the edges were like numbered differently, we see that every edge going into C could potentially give us new information about C, and we would update our priority, right? So the maximum number of times we can update the priority of a vertex is the degree of the vertex, okay? And a quick refresher, the degree of a vertex V is the number of edges connected to that vertex. So in this case, the degree of E is going to be 2, right? Okay, and then at least how many times? Well, we know that all the vertices start off with priority infinity, okay? And if the graph is connected and it's undirected, we know that there is a minimum spanning tree that contains all of the vertices, right? What this means is eventually we're going to have to add every vertex to the minimum spanning tree, right? This means that at some point we have to change the priority of a vertex, right? We have to change the priority away from infinity, which means we need at least one change priority operations for every vertex. And the reason for this, I mean, you guys can like look in the slide if you guys want to reiterate, but the quick thing is we have to change the priority of every vertex at least once, because every vertex is going to get added to the minimum spanning tree, and it's going to get added to the fringe by changing its priority. Or it's already in the fringe, but the priority of the vertex in the fringe will be changed. Okay, any questions on that? Okay, let's keep going. So yes, okay. Now we have like a couple options. We'll do a quick poll in like participants. Do you guys want to do more minimum spanning trees, or do you guys want to move on and skip these two questions on Kruskal/prims? Vote yes for do these questions, vote no for skip. Okay, it seems like most of the people want to move on, so we'll move on. And I'd encourage you guys to like look at these questions in your free time. They are good practice. Okay. Do you guys want to do bid questions? Vote yes for doing bid questions and no for want to move on. Yay, okay. We're doing bid questions. Here's the first one. It's basically, you want to perform the OR operation, but you can't use the OR operator. Okay, once you guys are done, you guys can put a green check next to your name. I erased all of the old green checks. Okay, we'll go for like another minute. Okay, for the sake of time, I'll show you guys some intuition of how you guys can get to the solution. Okay, let's look at an example. I think it's always best when you guys are working with bits to like start off with some example. So let's say we have, I don't know, 1, 0, 0, 1, and we have 0, 1, 0, 0. Actually, let's go like that. Okay, so after performing the OR operation, what we're going to be left with is 1, 1, 0, 1, right? I mean, that makes a lot of sense. So when we work with bit questions, we have a limited toolkit of potential stuff we can use, right? Let's just walk through all of the stuff we can do. We can do some sort of shifting. Shifting is not going to work, right? Shifting is like a totally different idea. Maybe we can do some XOR operation. Maybe. I don't see any like immediate use of it right now. Let's keep looking. What about AND? Okay. Well, AND is very similar as OR. Why is it similar? So when we AND two numbers together, right? If they're both 1, we keep the 1, right? If they're both 0, we keep the 0. The only difference with AND is when there's a 0 and a 1, the AND chooses the 0. With ORs, when there's a 1 and a 0, OR chooses the 1, right? So what if we flip all the bits, right? So what we can do is we can flip all of the bits. Now we have 0, 1, 1, 0, then 1, 0, 1, 0, right? Now what happens when we AND? Okay. So we'll call this flip. Okay. Now when we perform the AND operation, let's see what happens. And like the reason like I tried to do this is we know that AND does the same thing that OR does with 1s and does the same thing with 0s, right? So let's just try entering the world of 0s and see what happens. Okay, so after we AND these numbers together, we'll get 0, 0, 1, 0. Well, that's really close to the correct answer, right? All that we have to do is just flip the bits. So formalizing this more precisely in terms of code, what we're doing is we AND A, or we not A, right? We flip the bits, we not A, then we flip the bits on B, okay? Now we AND these two together, right? Now we take the result, and then we not, or flip the bits of the result. Oh my gosh, how did that happen? And then, did you guys learn about De Morgan's law? Yes, no? Okay. So if you guys think about De Morgan's law, when you distribute the not, this thing becomes A or B. But that's not like too in scope. Yeah. Okay. Does anyone have any questions on that one? Okay, let's move on. Yeah, same thing that I said. Do you guys want to do another big question? Do you guys want to move on to other stuff? This is a laser. Okay. Okay, let me think. I'll quickly test this and then I'll let you know. Okay, we'll start with bit. Oh, one more bit question. Oh. Yeah, okay, we'll do this next bit question. I thought you had a bit question, but I realized it's doing another bit question. Okay, and then Jeremy, I'll check if your solution works. Okay, once you guys are done, put a green check next to your name as per usual. Okay, I'm gonna go through it. Sorry, it took a second. Okay, does anyone want to give an answer, or do you guys just want to hear a solution? Slash how I got to the solution. Anyone want to say an answer? Okay, so let's walk through how like we could approach this big question on our own. So as per usual, let's pull up some examples, okay? These examples have kind of big numbers, so I'm gonna use my own example. Oh, perfect, we got an example. And num minus. Okay, this works. The only concern is that it violates the one subtraction addition operation. But it's basically the same thing that I'm doing. Like basically the same. Okay. So let's kind of like play around with it a bit more. So let's say that we have some numbers. Let's say we're doing 4 is the power of 2. How is 4 written? Right? And then let's say that we have, I don't know, a bigger number. Let's say 1, 0, I don't know, 0, 1, 1. Okay. what's this number? 1 plus 8 plus 16, 24, 25. Right? Okay. So after performing this operation, what should we get? Well, we chop off the last none, and then we get 24, right? Well, how did we do that? Well, let's see. All we did is we masked, what we did is we got rid of this 1 right here, right? Removing the 1 from 25 gives us the correct answer, okay? In other words, let's think of how we can use a mask, right? The idea of a mask is that we isolate certain bits that we want. Okay? So which bits do we want? Well, looking at this number, we don't care about these bits right here, right? We don't care about the 1 and the 2 bits because when we divide the number, right, we're basically chopping off these bits. So what we're doing here is we take any number, right? We take any number and we're ANDing it to remove the last however many bits, right? In this case, what we're doing is we're taking 25, which is written as 11001, and we're ANDing it with a bunch of ones up here and zeros down here, right? What this does is it removes these bits, right? And it spits out a number that's basically the original number minus the things that 4 doesn't divide evenly, right? This will spit out 24, okay? So the next question is, how can we create this mask, right? All we have to do is create this mask, okay? And we can successfully solve the problem, right? We take the mask and we AND it with the given number. So let's try to relate this mask in terms of the number 4, okay? We have this mask, and 4 looks like this, right? It has a bunch of zeros this way, right? Because it doesn't have any bits here. So we somehow have to take 4 and make it into a mask. Well, this is a bit tricky. Well, what happens if we take 4 and we minus 1, right? Taking any power of 2 and subtracting 1, right? So let's say we take 4, and then we subtract 1. Now we get 3, which looks like, okay, so now we're really, really close to getting our mask, right? You guys see that? All we have to do to get a mask is now we just have to not, or flip the bits on 3, right? So this is a -1 operation, and then this is a flip. Okay, so let me just double check. Yeah. So then this gives us the solution of we take our power of 2, right? We subtract 1. We flip the bits. This gives us our mask. We take this mask and we AND it with the given number. Okay. And a helpful thing to know is that when we have powers of 2 and we subtract 1, it gives us a number with all ones on like the right-hand side. That's like a helpful thing to just like remember because it does come up from time to time. Okay. That question was rather tricky, so no worries if it was a little hard. Any questions on that? Okay, no questions. So I prepared some more problems, so we'll go through the other problems. If you guys have to go, that's totally fine, but we'll see what other problems we got. Okay, we have some more graph questions. There's some of everything. Okay, so the first one is like a fun algorithm problem. I actually didn't come up with this problem. This is like, I usually don't copy questions. I try to make my own ones, but I did copy this one from something I saw in the past. Okay, once you guys are done, add a green check next to your name. I removed all of the prior green checks. We'll go for like another 30 seconds. Oh, actually, everyone's breezing through. Okay, so a lot of people seem to have some idea, so we'll take it up. Does anyone want to give out a solution? You guys can yell it out. MSD. So it's actually like a tricky problem. Think about a graph. This is more graphs for a reason. Okay, so Anish got it. The answer is we run a topological sort on a graph. Okay, so let's kind of like quickly explain that. When you guys see ordering, obviously you guys should think of sorting, but a topological sort actually produces an ordering, right? Let's say that we have some sort of alphabet. I don't know, let's say alpha is less than beta, alpha, let's say, I don't know, beta is less than epsilon, right? And let's do, what's another one? Actually, let's just do these two for now. In order to represent it as a graph, what we can do is we can put nodes for every tuple between alpha and beta or any other symbols. We'll create a directed edge in the graph, okay? What this edge is saying is that alpha must come before beta, okay? So then we'll add in these two, okay? So now what we're doing is we're given some graph like this, and we want to figure out a way to go over all of the vertices in the graph in order, right? When we think of some in order way of traversing the vertices in a graph, this is exactly what a topological sort does. Okay. And if you guys want a bit more explanation, the solution has like a few more words, but that's the gist. Does anyone have any questions? Questions? Okay, let's move on. So this last section isn't like that emphasized in the class, but I think these are really, really cool things to learn. That's why I wanted to add it. If you guys want to go, that's totally fine. But I encourage you guys to stay because this is very, very interesting in my opinion. It might like blow your mind to some degree. If you guys have questions, you guys can send them in the chat. Once you guys are done, you can put a green check next to your name, and I cleared all of the existing green checks. Okay, I'll give you guys another minute and then I'll walk through them. Okay. I'm going to take it up. Hopefully you guys had enough time to think of some ideas. Okay, so for the first one, I'll just show them all here. So the first one, if a vertex is weighted, we somehow have to consider the weight of that vertex, right? Like let's say that we have two edges. Okay, we have some vertex A, and let's say A has some weight 10, okay? How can we consider the weight of the vertex? Because currently Dijkstra's doesn't consider vertices with weights. So there's multiple ways of actually solving this problem. One way that we can do is that we can simply, like let's say that it had 1, 1, 2, we could simply add that weight to the incoming edges to A. right? Let's say that A is of weight 10. What we can do is we can add 10 to the incoming edges of A. Okay? This means that if in order to go to A, we have to incur the cost of getting to A, right? So that's one way of doing it. We could also add 10 to the outgoing edges, right? That's the same thing in this instance. Try to like prove to yourself why it's the same thing. Another solution, this is my initial solution, but I realize there's other ways of doing it, is that what we can do is we could take A and we could split it into like A1 and A2, and then have that edge weight between them be the weight of taking A, right? So it'll be something like that. So many ways of solving the problem. For the second one, let's try to like walk through how we can get to the solution together, because I think this is really cool. So let's say that we have two paths, okay? We have two paths to get from one vertex. Let's say we can either go like this, or we could take a bunch of intermediate vertices to get there, okay? Right? These are two paths, both of the same weight. So what could we do? Well, in order to break this tiebreaker, we somehow want to choose this 4 path, right? This is the path we want. We want to choose the path with less edges. So let's say that we add some value to every single edge, okay? Let's say that we add, I don't know, what's a good starting value? Let's say we add 1 to every edge, right? So then this could be 2, this could be 2, this could be 2, this could be 2, right? And then this one would be 5. Yay, that looks like it solves the problem. But it actually creates another problem. So what does it create? Well, let's see. Let's say that this edge was a weight 5, okay? And all of these edges are of weight 4, right? In this case, we want to take this path because this is the shortest path to get from U to V. They look the same. This is supposed to be a V, right? But notice that if we increment all of these edges by 1, right? This thing will go from 5 to 6. Now we'll be taking this path instead, right? That's incorrect because we only want to choose the path with less edges when they're the same cost, right? Do you guys see that? Okay. But we seem to be thinking along the right track, right? Let's go back to the initial example. It made sense that we wanted to add some value to all of the edges. The only problem with it was that we added the value that was too big, right? 1 was too big of a value. So let's say that we add, I don't know, 0.0001 to all of the edges, right? Right? We can add 0.0001 to all of the edges. And then this would work, right? Because then we wouldn't choose the path that isn't the shortest, right? The only slight problem with this is we can just create like a massive graph in which this is incorrect, right? It's not enough. Or it might be like too much change and then we get the incorrect answer. So what we should be really doing is we want to add some number that's in proportion to the number of vertices on the graph, right? Because the problem with adding 0.0001 is like, let's say the graph is huge, right? Then we might run into the same problem of adding 1 to each vertex, right? We could run into that problem again if the graph gets massive. How do we solve that? We want to add some constant that's proportional to the number of vertices in the graph, right? Let's say we add 1 over n. And let's say n is the number of vertices in the graph. Okay? This will actually work. Because this constant, if you guys think about it to yourself, will never be too much. It'll never like allow us to choose the path that isn't the shortest. It'll always just be enough to like provide a tiebreaker. Right? So the final solution is that what we're going to be doing is we'll add 1 over n, where n is like the number of vertices to each edge. So now when there's a tie break, we can choose the proper path to take. Does that kind of make sense for everyone? Okay, I think that was a really cool answer. When I first learned of how to solve problems like this, I was a little mind blown. Okay, so the last one is we can start from any vertex in a subset of vertices. So let's see what that is. Let's say we have some subset of vertices, and we eventually want to get here, right? We can start here, here, here. Okay, so this is tricky, right? How do we choose which one to start from? You know what would be really helpful? If there's some vertex that all of them were connected to, that connected to all of these vertices, right? Then we can just start from here, and then this vertex, let's say the shortest path happened to be right here. Then the shortest path from this vertex to here would also be along that path, right? So what we're going to be doing is we'll create some sort of dummy node. Okay, a dummy node is just something to help us solve the problem. That's what a dummy node is. And what we'll do is we'll connect the dummy node to all of these vertices with edge weight 0, okay, to each vertex in that subset. Now what we're going to do is we'll run Dijkstra's from this dummy node, okay, till V. And this will work. Why will this work? Because the dummy node will choose, right? It can either go through this vertex. It can either go through this vertex or this vertex, right? So it'll choose the optimal start vertex for us, and we don't have to do any work, right? What if we run Dijkstra's from view? Okay, so that could work. The only problem with that is we'd have to flip the edges. We'd have to flip the edges. Yeah, that could also work. And then another way, in order to make you use the dummy node strategy, I could say that there's a subset of vertices that you want to go to, right? So now you start from a subset of vertices and you end up in any one of the subset of vertices. Then you'll have to choose the dummy node strategy. Yeah. Okay. So that's all I created. Good luck for you guys' final exam. I just wanted to say a final goodbye. It's been a really good semester. This is my first semester as a TA, and I've had an absolutely amazing time. So I just want to thank you guys for consistently coming every week and allowing me to rant about all of the intricacies of 61B. So yeah. All right. That's all. If you guys want to say a bit more to talk about whatever, you guys can feel free. But that's all I had prepared for today. Yeah.
Appreciate it, so thanks.
Yeah, I appreciate you guys coming all the time. It's good. I'll buy you chocolates. That's funny. You don't have to give me anything. If you guys get an A, that means I get an A as well. By association. Yeah.